Hi everyone, welcome to this video, and we're going to look at an electromag question again, and we're going to look at the net electric field and direction at a point due to 2-point charges in 2D. Now to start off, the equation that we need is the electric field is equal to the force per unit charge. The force comes from Coulomb's law, which is Coulomb's constant Q over R squared times by the Q. And we're left with the Q in question that we can calculate with. Now, so we've got a point charge at 3, -1, these are coordinates, another point charge at 2, 3, and it's asking what is the electric field and direction at -1, 2. So, to start off, I'm going to draw a graph in the X and Y direction. Here's Y, here's X. We've got 1, 2, 3, -1, -2, -3, -1, -2, -3, 1, 2, 3. Okie dokie. Q1 is at 3, 1. 3, 1 is Q1 with -2 microcoulombs. Q2 is at 2, 3 with 3 microcoulombs. 2, 3. Q2, which is 3 microcoulombs. And the electric field at -1, 2 is the point in question, which we'll call P. Okay. The electric field is additive in the sense that the vector of the electric field from Q1 and the vector from the electric field at Q2, if you sum them both together, you'll get the electric field at point P, if you're working with the distance between them in the equation that we just derived, this one. So, the electric field at P, which is a vector, equals the electric field due to 1 plus the electric field due to charge 2. Okay. So let's do E1. E1 is a vector. From the equation before, we can see that it equals K, Q1 over R1 to P, point P squared in the R1 direction, the unit vector, because we were asked what was the direction as well. And the unit vector is simply the vector in question over its magnitude. Nice and simple. So, E1 is equal to Coulomb's constant times Q1, which is -2 microcoulombs, over R squared. In this case, R squared is 1, 2, 3, 4, -4 in the X direction, and 1, 2. Oh, sorry, from here, 1, 2, 3, plus 3 in the Y direction. So R squared is going to be the magnitude of the vector, which is -4 squared plus 3 squared. Now the unit vector is going to be -4i plus 3j, because that's the vector from Q1 to point P, which is this part here, over the magnitude, which is -4 squared plus 3 squared, square rooted. And from a calculation earlier, this gives me 576i minus 432j. So we'll bear that in mind. For E2, it's exactly the same calculation, except we use Q2, and the radius squared, sorry, the distance between them squared and the unit vector is different. So it's K, Q2 over R2 to P squared. Sorry, let's get rid of that. The unit vector is R2. This, of course, is equal to K, 3 microcoulombs, which was the charge of Q2. The distance between Q2 and point P, which is minus squared, which is minus 3 squared plus minus 1 squared. And the unit vector is, of course, minus 3i minus 1j over minus 3 squared plus minus 1 squared square rooted. And this, in fact, comes out to be minus 2,561.4i minus 853.8j. Okay, so we've got our vectors for E1 and E2. All that's left to do is to add them together, and what happened to my piece of paper I will never know. So let's get another quick one. So EP, the vector, is equal to E1 plus E2, and we end up getting minus 198.5.4i minus 1285.8j. Okay, this is great because if we look at our graph, we can see that EP goes in the negative I direction and the negative j direction, which means EP is this way. Awesome. And to get the magnitude, all we have to do is, sorry for the paper amount, there it is, all we have to do is square it and square root it. And it gives you a magnitude of 2365.4 newtons. I believe so. Yep. And it's as easy as that. You've got the direction, because you've got it in vector form, you've got the magnitude, and if there was a follow-up question asking if there was a charge at point P, what is the force? Then you can simply use the equation before of F equals QE, and you can use EP in that equation because it's at that point. Nice and easy. I hope you enjoyed the video. If you've got any questions or feedback, please put it below, and I'll see you next time.